In this video we're going to look at a couple of different metrics that we can use in order to work out how well our CPU is running. Also, it allows us to compare different algorithms. So if you like, we can use it as a benchmark in order to work out whether one algorithm runs better than another algorithm. So don't worry too much if you don't understand what was on this page here. Whenever we open up the assembler debugger, it'll be quite straightforward. So the first one we're interested in is CPU time. Now this is quite a straightforward one. If we start a program, we start our stopwatch. When we stop the program, we stop the stopwatch. So this is the length of time it's taken for the program to run. So this is going to be the total number of clock cycles that are in a program times the length of each clock cycle. And the length of each clock cycle is dependent on the frequency of the clock. So that's quite straightforward, that one. The next one is the cycles per instruction. So the cycles per instruction is the cycles per program divided by the instruction count. In our computer, the CPI has a value of 1 because we only have one cycle, that is one fetch execute cycle per instruction. There aren't any instructions in our computer which have any more than one fetch execute cycle. But in an average computer that isn't the case. So what you could do is you could work out an average cycle per instruction. So the average cycle per instruction would be given by something along these lines. We could work out the percentage of ALU instructions in a program and the number of cycles, and the percentage of load with the number of cycles, and the same with the store and also with the branch or the jump instructions. And then we can work out an average of our cycles per instruction by multiplying this 0.5 by 4, 0.3 by 5 and so on and so forth, and this would give us a value of 4 cycles per instructions. So there's going to be on average 4 fetch execute cycles per instructions in an average computer. Now in our computer we've actually got a very good value. We've got a value of 1. But we could have it with computers that have values of fetch execute cycles that might even be less than 1, because if you had multiple cores and also you were able to load or run the program in parallel via each of those cores, you could actually get the CPI value to be less than 1. So there's a bit of a mouthful here. It's best seen by example. So let's go ahead and we'll open up the assembler debugger that's in the resources section, and we'll have a look at these two values. Open up the assembler debugger that's in the resources section. Now whenever you open that up, you'll see that we've got some extra information up in the top right hand column here. So we'll talk through that in just a moment. So what we want to do first of all is clear off the information that's already on it. So press the clear button and then get into the sample programs, and we'll pull out the second one along here, which is the unsigned multiply shift. So Control C there and Control V. Now before we do anything, we'll just actually assemble it and we'll run it. So I'll hit assemble and hit the debug and press the escape button, and it will run through a little bit quicker. So you can see the numbers up here changing as it runs through the program, and that's it finished now. So let's go ahead and we'll look at what some of these numbers are telling us. So the first one here is the value of 23, and that's just a count of the number of bytes that are in the program. So in this program we've got 23 bytes. So the 23 bytes, we can just count them actually from here if we like. We can say there's going to be 1 byte for the data R0 and another byte for this number here. There's going to be 1 byte for the data R1 and another byte for this. So we could count the number of bytes as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 and 23. So that's our 23 bytes of our program. So that's quite straightforward. Now the other one we're going to look at here is the instruction count. So the instruction count's the column N. So this is actually the instruction register. So this is the number of instructions that we have to go through in order to run through the entire program. And we can see here that we've actually worked through a value of 78. So that's the number of instructions. The CPI value, or the cycles per instruction, now remember this is a fetch execute cycle per instruction, is a value of 1. So for every instruction that we have in our CPU, it takes 1 fetch execute cycle in order to complete it. Now as we said before, that's not normally the case. Normally the case would be that it would take more than 1 fetch execute cycle to go through more complicated instructions, but because our instructions are quite simple, we can go through this and these are all of our instructions in just 1 fetch execute cycle. Now the next column here are the actual number of clock pulses that it takes to get through our fetch execute cycle. Now we know we've got a value of 24. If you get into the CPU and then head into the control section, we'll see that we have the stepper, and the stepper controls the flow of information around the CPU. So we're going to have 4 clock pulses between each of these. So we're going to have 4 clock pulses from here, so that's 4, 8, 12, 16, 20, 24 and back to the beginning. So it's going to take 24 clock pulses to do the fetch execute. So the fetch is done in the first 3 lots here, and the execute is done on the remaining 4. So we've got 24 clock pulses in our fetch execute cycle. In order to work out the total number of clock pulses it takes for this program to run, it's going to be quite straightforward in our machine. We need to multiply out the instruction count, which is 78. So there's 78 instructions that have been effected here, and we know that we've got 1 fetch execute cycle per instruction because our CPI value is a value of 1. So we can work out this number of clock pulses simply by multiplying the 78 by the 1 by the 24, and it's going to give us 1872 clock pulses. Now if we wanted to turn this into an actual time value, we would have to decide on a particular clock speed. So let's say we decide that our clock is running at 4 megahertz. Now this is just a random value that I've picked out, so we're kind of going back to early 80s CPUs. So what we can do then is we can multiply the number of clock pulses by the length or the time it's taken for the clock pulse. Now the time it's going to take for the clock pulse is going to be 1 divided by 4 million, and that's times this 1872. So that's going to give us this value here in seconds. So it's 0.000468 seconds it's taken us to run through this multiply command. So that's going to be 468 microseconds. Okay, so where are we going with this and what's the point? Well, we have got a multiplication which is done by software. So it's an algorithm we've written in order to do the multiplication, and it's taken us 468 microseconds. Now if I was going to do the addition is actually hardwired into the CPU. So in order to do the addition, I just simply need to put in add, say R0, R1, and the addition is only going to take up 1 byte of memory, and it's only going to take up 1 fetch execute cycle, and 1 fetch execute cycle is going to be 0.000012 seconds. So you can see here that the add instruction, which is hardwired into the machine, is going to run an awful lot faster than the program that we've written in order to do a multiplication. And also it's going to take up a lot less memory. So that would suggest to us that it's much more efficient in terms of memory and also in terms of the speed if we were to hardwire the instructions into the CPU. That is, if we were actually to go in and build the logic circuits within the ALU to perform the, say, the multiplication and also the division. So what we're really talking about here is that in this instance here, it would be much better if we were to have a more complex instruction set. So that is, we would have a Turner machine from a reduced instruction set machine, which we've got at the moment, and into a complex instruction set machine, which is sometimes called RISC and CISC. So the add instruction will run about 40 times faster than the multiplication algorithm that we've had to write. So this means that whenever we design a CPU at first, we really want to make sure that the instructions that get used most often are actually hardwired into the machine. And we can see this in particular whenever you're looking at DSP processors, because they do an awful lot of add and accumulate, so add and multiply instructions. That's just the nature of the mathematics of digital signal processing. So it's obviously much better to hardwire something than it is to write a code using the non-hardwired version. So we can use these metrics here in order to work out how quickly an algorithm runs and compare one algorithm to another. So that's all there is for this video. I suggest you write a few algorithms yourself and check and find out the speed of execution. You could also go in and change the frequency here and stick in different frequencies and just mess about with it and make sure you understand this CPI value and how we were able to get to this final time here for each of the algorithms. So thank you for listening. I'll get you on the next video. Goodbye.